Now what we want to do is look at a first law analysis, and let's take something, our system, it'll have air going in, it'll have fuel going in, and we'll call these, we'll say this is the enthalpy of the reactant, so we're just going to lump them together. We'll have the products come out, and we'll have this be the enthalpy of the products. So we use that terminology. There could be some power produced, and there could be, as we saw, Q dot going in. So this is normally what we have. Most often, H sub R is at STP. So most often, it's around that, so we don't have to worry about it. Most often, the products leaving an engine, a furnace, are not, they're at higher temperatures. So this, not at STP, but higher temp. Everything could still be at the pressure, but the temperature is different. So now what we want to do is write a general first law equation that enables us to find the change of enthalpy for elements in compounds. And so let's look, so the general first law, I have Q dot plus the sum of the reactants, N dot F times H sub F bar 0 plus H minus H298 of the fuel is going to be equal to the power plus sum for the products of N dot J times H sub F bar 0 plus H minus H298 of J. And so what happens is we saw that the H sub F bar zeros we could find in table C1. So C1 gives us the H. And so, but what happens is if the temperature is greater than that, then that needs to be changed. It's like I also have an energy associated with the compound being at a temperature other than 298. And in the products of combustion, remember we might have oxygen and nitrogen there, and those could be at a temperature other than 298. And so we need to be able to account for that. So this delta H is the correction for the temperature above 298. And these are found in table C2. So the delta H is found in table C2, page 844 and following. And so, just so you have an example of that, turn to that page, and for instance, for nitrogen at 1,000 degrees K, you should find that delta H is equal to 2140, 400 kilojoules per kilogram mole. And you should find for CO2, and for CO2, you're at 1,000 degrees K, you'd find that delta H is equal to 33,405 kilojoules per kilogram mole. So we can look those values up. And now what I'd like to do, and so make sure you can find them. And now what we're going to do is look at a problem, example 12.8 that's in the text, and we'll go through balancing the equation and doing the first law analysis for it. So read the problem because they are words. I'm just going to write down the solution. So we have a diesel engine. It's going to receive dodecane C12H26 has air. These are at 25 degrees C, 200% theoretical air. We are going to want to find the power. The products leave at 600 K, and Q dot is equal to 232,000 kilojoules per kilogram mole of fuel. And so what we're going, and we want to find the power, so we need to find the power. And so what we have is fuel coming in. We have it at 200% theoretical air. It's going to come out. We're going to have to balance the equation. We're going to use our first law analysis because we'll know Q dot, we'll find all these delta H terms, and we'll solve for the power. So if we balance the equation, we have C12H26 plus 18.5 times O2 plus 3.76 N2 yields 12 CO2. So this is going through and balancing things as we've done before for the conservation of mass. So you know how to do that. Plus 13 H2O. And you can read the example problem in the text if you don't. Plus O2 plus N2. Now, what happens is 18.5 balances this for 100%. We have 200%, so I need a 2 in front of this. And so that gives me 200% theoretical air. And here we have 18.5. And the nitrogen number is 139.12. So that gives me the balanced equation. So now that's going to give me the numbers, like I'll have 12 CO2. Anyway, let's go through and solve for this. So the way we write the first law equation in general is we have Q plus HR is equal to W plus HP. Now there's no flow rate here, so if I multiplied by the fuel flow rate, I would have this on a time basis. So if I multiply this by N dot F, I would have that, but we'll hold off momentarily for that. So H sub R is equal to H sub F bar 0 of the dodecane, C12H26, and it's equal to minus 290,971 kilojoules per kilogram mole. If I look here, because it's at 25 degrees C, the enthalpy of elements at 25 degrees C is 0. So the 0 here is 0. There's no energy contribution, no enthalpy contribution from the elements. For the products, though, we have a whole bunch of stuff going on, so I need to erase some things here. So H sub P. So we have 12 moles of CO2, 12 times the H sub F bar 0 minus 393,757. So this is the H sub F bar 0 of CO2 plus the delta H term, which is 1,212,916. So I'm going to do this for each of the terms here, evaluated at 600 degrees K. Plus I have 13 for the water times minus 241,971 plus the delta H is 10,498. Then I'm going to have the oxygen and the nitrogen. So I have plus 18.5 times the delta H, 9247. And this is for the O2. And this is for the H2O and the CO2. And then I have it for the N2 plus 139.12 times the delta H, 8891 for the N2. So if I do that, I get H sub P is equal to minus 6171255 kilojoules per kilogram mole. And now if I substitute in the equation that we had for Q plus HR, so if I use that equation, so if I do Q plus HR is equal to W plus HP, we're going to have minus 232000 minus 290971 is equal to W, which we don't know, plus a minus 6171255. And so if I solve for W, you end up with these really big numbers, is equal to 5,648,284 kilojoules per kilogram mole. And if we have the mole flow rate of 1 kilogram mole per hour, N dot F per hour. So if I divide by 1 divided by 3600, it's going to give me per second 0.30123 kilograms per second, kilogram moles per second. Then we have W dot is equal to N dot F times W. And so with that we have 1569 kilowatts. And most problems require that we're either going to solve for N dot F, the power, or Q dot. So almost all the problems involve one of those three variables.